Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at sequential reactions. These are essentially reactions where I can break down an overall reaction into a series of elementary steps. So it turns out that most of the reactions we're familiar with, like the decomposition of ozone to oxygen, doesn't actually proceed according to the equilibrium equation we generate. Most of the time, it occurs as a set of smaller reactions. These are going to be our elementary steps. So the first step is ozone breaks apart into oxygen, molecular oxygen, and atomic oxygen, O2 and O. This atomic oxygen can then go ahead and recombine with another ozone molecule floating around to generate two more species of molecular oxygen. And so in this case, one of the things we have to watch out for is the formation and consumption of what are called these intermediate species. So one of the key features of these intermediate species is that they don't appear in the overall reaction equation. So think about with redox reactions with electrons. We never can really isolate those electrons, but we do know that they move from one species to another in order to generate a product. So one of the big things is that the intermediates can often be isolated, so we can confirm their existence, but they're also very typically short-lived. And as a result of this quick consumption, it's often hard to determine their concentrations, which will play a role when we're trying to generate overall reaction rates later. So let's go ahead and take this overall reaction and split it up into its individual elementary steps. So the first step is going to be the formation, the consumption of ozone to make molecular and atomic oxygen. And it's actually going to have a fairly simple rate. It's going to be the forward rate constant times the concentration of the reactant, in this case, just ozone. So this first reaction, since it only has one reactant molecule, is said to be unimolecular. And a big feature of unimolecular elementary reactions is that they should be, lo and behold, first order, as they only depend upon the concentration of a single species. However, in comparison, the second reaction is going to have a rate constant of K2 and depends upon the concentration of both ozone and atomic oxygen. As a result, it's said to be bimolecular, as it depends on the concentrations of two reactant molecules. Now, one of the key features to note about these bimolecular reactions is they will be second order overall. However, they could be first order in individual reactants. So it's also important to remember that if I had a reaction elementary step that goes 2A to B, this would also be said to be bimolecular. Only big difference here is that both of the reactants are the same species. And you'll often see people, as a result, for additional clarity, to write this instead of 2A goes to B as A plus A goes to B, to really emphasize that we have two different molecules colliding in order to form a product species. Now, one of the key features that we're going to try and look at is how we can combine these various elementary rates in order to determine an overall rate. Now, one of the real problems with this is that it turns out the exact method of figuring out what the overall rate is going to depend, simply put, on which step is faster. Is my first or second step going to be faster? These are more commonly labeled as the fast step and the slow step, especially if the rates of reaction are significantly different. Now, one of the big things to note is that a reaction can only proceed as fast as its slowest step. So as a result, the slow step is often labeled the rate limiting step, because since it's going to control how quickly molecules move through the system, it's going to control the overall rate. So in this case, think about a river flowing downstream, and it has to go through some sort of weir or thinning of the stream bed. This is going to determine exactly how fast water can move through the overall stream. And it's the same case with these reaction rates. So let's go ahead and take a look at an example where the initial step is the slow step in a two-step reaction. And we can see this with the reaction of hydrogen gas with iodine monochloride. So in this case, we have one hydrogen gas molecule reacting with two iodine monochlorides. And the first step is going to be the slow one, getting hydrogen to react with the iodine monochloride to form HCl and HI. Now, once we've formed HCl and HI, this hydroiodidic acid can go ahead and react with my iodine monochloride to make I2 and HCl. As a result, I have my overall reaction. However, it turns out once I form that hydroiodic acid, it will quickly find any sort of ICl molecule, and this second step goes fast. And so as a result, my concentration of hydroiodic acid will often be very low and will be immediately consumed. So as a result, any kinetics after this slow rate limiting step can really be ignored, because whether this reaction goes a little bit faster or a whole bunch faster, it doesn't matter, because pretty much as soon as I've done this first step, everything else just goes straight to completion much more quickly than I had to get there in the first place. So as a result, the overall rate of the reaction will be determined just by that first step. So the rate of the reaction will be based on the this rate of this first reaction, with a rate constant of the first rate constant and first order in hydrogen and first order in iodine monochloride, not the second order we would have expected from the overall reaction. And this is one of the reasons why it's very important to know the exact elementary steps in a reaction. Now let's go ahead and compare this to what we'd expect to see from the potential energy diagram for this reaction. So we start here with our reactants, and we have to go over that first transition state to generate our intermediate species. So this is how we end up generating that initial HCl. However, once I form that HCl, it has a very low activation energy, so a very fast rate for the second reaction. So pretty much as soon as I get past this first big hump, it's very easy to get past the second one to generate products. And this illustrates several important features. One of the things that makes it so that we can actually isolate intermediates is the fact that they form what are called a local minimum. This means that there are a small little divot in our potential energy surface, so we can have molecules that will rest here for a little bit of time before they get enough energy to go over the next step in the reaction. And but more importantly, one of the things that really pops out here is that our rate is typically controlled by the highest energy transition state. Whichever transition state is the highest in the energy surface, this is going to be the one that's the most difficult to get past, and afterwards everything is pretty much downhill. And this is generally what we see. However, we do have slightly different dynamics when we have a slow second step, and we see this in the case of ozone. It turns out that ozone, especially in the presence of light, will quickly decompose into molecular and atomic oxygen. However, that atomic oxygen then takes a little while to find another ozone molecule in order to complete the reaction in forming molecular oxygen. And so in this case, it's this reaction of ozone with atomic oxygen that's the slow or rate limiting step. And as this step is fairly slow, it means we can build up a fair bit of that atomic oxygen in the meantime. In fact, we can have enough buildup of that atomic oxygen that it will have a chance to react with some of the molecular oxygen reaction, and we can reform the ozone. In other words, this first elementary step might not be one directional. It may actually be able to go forwards or backwards, which gives us another elementary step. The first one, the reaction of ozone to make our molecular and atomic oxygen. And the second elementary step, the reverse. And then our third one, again, that ozone and molecular oxygen driving the reaction to completion. And this is going to provide some interesting dynamics for the overall rate of the reaction, again, using this new elementary step mechanism. And again, noting that this tends to happen for any steps before the slowest or rate limiting step. They will end up proceeding both in a forwards and a reverse direction. And just like before, we're going to find the rate will be controlled by the slowest step, in this case, the second reaction. So our overall rate will be determined by the rate constant for this second reaction and the concentration of both ozone and atomic oxygen. However, it turns out it's really hard to figure out what the concentration of atomic oxygen is, as this is a relatively radical species, and I do mean that as it has unpaired electrons, making it very hard to be isolated, and its concentration's really not easy to measure. So we're going to need to find another way to describe the concentration of this intermediate. And again, this is actually going to be common for a lot of intermediate species. So what we're going to want to try and do is find a way to report the concentration of this intermediate solely in terms of reactants and products. And this gets a little bit tricky. However, one of the easiest ways we can do this is to assume that this initial cleavage of the ozone, it goes all the way forward and then backwards and forwards and backwards, and it essentially reaches an equilibrium with only a very small amount of that ozone being pulled out of the equilibrium to drive the reaction to completion. In this case, we say that this first reaction has gone to equilibrium. And I'll always try and be very clear whether a reaction is just simply reversible or goes to equilibrium. However, if it does go to equilibrium, we know how to treat this. We can use our equilibrium constant, which last time we showed for any elementary reaction is just the ratio of the rate constants as well as the ratios of products to reactants. But now we have a very powerful feature. I know how to relate the concentration of that atomic oxygen to the other two species. I can isolate its concentration. I can then feed this concentration of my atomic oxygen into this rate limiting step to get an overall rate for the reaction. So the rate for the reaction will depend upon the rate for the second reaction, the equilibrium constant for the first. We're second order in ozone, and what's this? We now have the concentration of oxygen in the denominator. And this means that the reaction is negative first order in oxygen. That is not a typo. This is actually something that happens. What this means is that as I increase the concentration of oxygen, the reaction rate actually goes slower. And this is a common feature in a lot of reactions. In this case, what happens is that it turns out that molecular oxygen acts as an inhibitor to the decomposition of ozone. If I have too much of my product, the reaction just really won't proceed at all. And this actually does happen somewhat frequently with a lot of different species. And really why this happens is that as I have too much O2 in the system, not only is it just a product, which doesn't really matter, but it turns out that if I have too much molecular oxygen, that atomic oxygen, instead of reacting with ozone, reacts with O2. And so this will slow down the reaction as less and less of the oxygen can go towards completion. And it turns out that this is how most chemical inhibitors work. You can slow down a reaction by having some sort of process that essentially consumes a reactive intermediate, preventing the reaction you actually want. And this is something important to keep in mind. However, next time, we're going to go ahead and dive in a little bit more in detail to figure out how we can solve for the overall rate of reaction if this second reaction isn't quite so slow that I can consider the decomposition of ozone to go to completion. Until then, take care.